All right, now let's continue. One example for using this inverse Laplace of what is it? Convolution. So as we know, Laplace transform of convolution of f and g is just equal to the product of the transforms, right? That is capital F of S times capital G of S. Now, if you consider this example, let's say 2k cubed and over s squared plus k squared squared, right? And we have seen this example earlier. We know that Laplace transform of this function on the left, right? This function is equal to 2k cubed over s squared plus k squared squared. Anyway, so now let's consider this example now. As an example, let's say we are given this, right? So here our f, whatever it is, f of s, that's equal to 1 over s squared plus k squared squared. All right. So the question is, what is the inverse Laplace transform of this function? 1 over s squared plus k squared squared, something squared, right? So to solve this one, again, we are going to use the theorem. Before doing this, in our first step, if you just notice here we have something squared, right? So if I just take this one, f of s equals g of s, that's equal to 1 over s squared plus k squared. Now what we have here? Here we have f of s times g of s then. That is equal to 1 over s squared plus k squared times 1 over s squared plus k squared, and which is equal to this thing, right? Okay, now from here we can find here, what is it? Our original function f of t. And here, what is f of t? Or since these two functions are equal, that is g of t, right? That is equal to 1 over k, because here we have k squared. And if I just put here k, we know that that is Laplace transform of sine of kt, right? So here we have inverse Laplace of, I can write here k over s squared plus k squared, right? So now we are familiar with this thing, right? I just multiply by k and divided by k to have this in suitable form. So here we have 1 over k, right? Inverse Laplace transform of this function is equal to sine of kt, right? So in this case, number 2, let me just change my marker color. Then inverse Laplace transform of this function, right? What we have here then, that is 1 over s squared plus k squared squared, right? And I can just write it as, here we have, what is it? Here we have k, right? That is 1 over k squared. I just multiply by k squared here and divide by k squared. Here we have Laplace inverse or inverse Laplace. Here I have k squared, so I can just write it as k over s squared plus k squared times k over s squared plus k squared, right? If you just multiply them together, here we have k squared over s squared plus k squared squared. So here we k squared, they cancel each other because k times k, that's equal to this. So now here we have f of s, right? And here we have g of s, right? And this thing, we know that is equal to f convolution g, right? And which is equal to, what is f convolution g? What is our f function? F function is this, right? So we can write it now as 1 over k squared integral from 0 to t. Our f function is sine, right? That is sine of k tau, because here we have f of tau, times what we have here, g of t minus tau. So here we have g of, actually g is sine. I don't have to write here g. So here we have g function is sine, and here we have k, here we have k. Instead of this tau, now here we have t minus tau. And here we have d tau, right? So we have to evaluate this thing. And it's just integral, to evaluate this thing, right? Now we need to just evaluate this integral. And from calculus, we know how to evaluate this. We had just product of two sine functions, right? Sine of alpha times sine of beta. Using the property, we can evaluate this. Okay, so next slide. I need one empty slides or space to do this. Okay, duplicates and clear this. All right. Okay. From the last thing, how do you evaluate this? If you remember from trigonometry, we have this property. Let me change my marker color. Here we have sine of alpha times sine of beta, right? That is equal to 1 over 2. And here we have cosine of alpha minus beta minus cosine alpha plus beta. And using this property, right, I can just change this thing into product. Here we have sine of kt times, here we have sine of kt minus tau. Actually, here I need to have tau, not t. Okay, here we have c k tau. And here we have sine of alpha, and here we have sine of beta, right? So that's equal to 1 over 2 times cosine of alpha minus beta. What is it? If we have k tau, and this minus k tau, right? If you simplify this, what we have here, k, right? And k is a common factor. Tau minus t minus tau. That is 2 tau minus 2, t. 2 tau minus t. Minus cosine, again, k is a common factor here. If you add them, tau plus negative tau, that's equal to 0. And here we have only t. So I don't have to put this parenthesis here. So here we have only cosine of t. Okay. So now if we substitute there, what we got here? Then Laplace Laplace inverse of, here we have 1 over s squared plus k squared, right? That is equal to 1 over 2k squared, because of this 2 takes out. And in the example here, we have 1 over k squared, right? Now here we have 1 over 2k squared, right? And here we have integral from 0 to t, right? And instead of these two things, I can just write this. So here we have, what we have here? Here we have cosine of k 2 tau minus t minus cosine of kt, and here we have d tau, right? Now we know how to evaluate this. It's just equal to 1 over 2k squared. It is just cosine function. Our variable is here tau, right? So it is 2k. I can just write here 1 over 2k times what we have here, sine of k 2 tau minus t. Minus, how about here? That thing is equal to this one here, kt, right? Kt, it is our variable, independent variable is tau. It's nothing to do here with respect to tau. It's just a constant function. So here we have tau times cosine of kt. And this tau changes from 0 to t. Equals, now if you evaluate this integral, what we have here? Here we have sine of kt. Why? Because of this one. Just substitute here. Kt minus k times t times cosine of kt over 2k cubed. Okay. because this kk, 2k cubed, and just evaluate, put substitute t for tau, 2t minus t. So here we have t, that's why here we have 2kt, and here we have, when it is 0, that's equal to 0, and just evaluate this integral, we got this answer. Okay. And in the exam, maybe I'll ask a bit simpler question, but at least you need to know the idea and how to evaluate this stuff. Okay. That is another example related to convolution. All right. Guys, the last thing now we're going to talk about periodic function. Okay. That is the last concepts here, and I will finish this course, this semester. Transforms of periodic function. And from, again, trigonometry or calculus, you know what we mean by periodic function. If a periodic function has a period capital T, where T is positive, right? Then we know that f of t plus capital T is equal to f of t. If this equation is satisfied for every positive t, right, then we say that this function f of t is periodic function. And this capital T, it is called a period of this function, right? So transform of a periodic function here. If f of t is a piecewise, again, piecewise continuous on this interval, and of exponential order, this guarantees that it has, what is it? Transform, right? Laplace transform. And periodic with period t, the third condition. The first one is f must be piecewise continuous on this interval. And second one is it must be of exponential order. And one more thing, periodic with period t. Then Laplace transform of such periodic function is 1 over 1 minus e to the power minus st times 0 with t times e to the power minus st f of t dt. Okay. Now proof is, again, directly we need to just use the definition of Laplace transform. All right. Because here Laplace transform of f of t. And why is it so? Here, Laplace transform of f of t, right? That is equal to using this periodic function, right? First, let's just write the definition. That is from 0 to positive infinity, right? Here we have e to the power minus st times, here we have f of t dt. Okay. Now, if I just write it as from 0 to capital T, because period is T, right? After capital T, again, it's just repeating the same thing. So here we have e to the power minus st and f of t dt plus from capital T to positive infinity. Here we have e to the power minus st. Here we have f of t dt. Okay. All right, give me a second. I need more space. All right. So what happens here? Because of t, right, as a period, maybe you are talking about some kind of function like this. Okay. Here, this one is t, and this one is 2t, and it can continue. This one is 3t, maybe. Maybe our function is something like this here, right? And after that, from t, again, repeating itself. And from here also, repeating itself, right? So that's a period. First, I'm just integrating from 0 to t, right? And if it integrate from t to 2t, we get the same thing, right? And that's why actually I just split this integral into 2. And after that, we just use, again, substitution. Assume that here t is equal to u plus capital T. Okay, u plus capital T. What happens here then? Here we have capital T to positive infinity, and here we have e to the power minus st, and here we have f of t. That is the second part of the integral, right? And I can just write it as from 0 to positive infinity, because using this thing, right? As here, if I just change t with u plus t, when t is equal to this t, right? T is equal to 0, right? When u is equal to 0, here our t is capital T, right? And when u goes to positive infinity, and also t is going to positive infinity. So that's why if I just make this substitution, let's say t equals u plus capital T, we know that capital T is a constant number. So that is a variable here. This is a variable here. When t equals capital T, then u becomes, what is it? 0. So u is changing from 0 to positive infinity, right? So now here we have e to the power minus s. Here we have t. What is t? U plus capital T. U plus capital T times what we have here. Here we have f of u plus capital T. That is equal to, du. This thing is equal to, here we have e to the power s times t. It has nothing to do with u, right? We can just take this out. So here we have e to the power minus s, capital T. Here we have integral from 0 to positive infinity, e to the power minus s u. And that is a periodic function, right? Instead of this, we can write f of u. And here we have du. And what is this thing? It's just Laplace transform of this function, right? That is equal to e to the power minus st, right? Times that thing is Laplace transform of f of t, right? So now what we got here? Here we got Laplace transform of f of t is equal to integral from 0 to t, right? Here we have e to the power minus st, f of t dt, right? And plus the second part from t to positive infinity is equal to this thing. Substitute here, e to the power minus st times Laplace transform of f of t, right? Now, if I just take this to the left-hand side, what do we have here? Here we have L. This L is a common factor. Laplace transform of f of t. That is a common factor. Here we have 1 minus, here we have e to the power minus st. That's equal to, on the right-hand side, integral from 0 to capital T, e to the power minus st times f of t, and here we have dt. Now, if we divide both sides by this, so here we have the Laplace transform of f of t will be equal to 1 over 1 minus e to the power minus st times integral from 0 to t, e to the power minus st, and here we have f of t and dt. Okay, that is the proof of the theorem. Why the Laplace transform of the periodic function f is equal to 1 over 1 minus e to the power minus st times integral from 0 to capital T, e to the power minus st times f of t dt. Okay. Then let's see one example for this and finish our class. Transform of a periodic function. Find the Laplace transform of the periodic square wave function shown in the figure below. Here from 0 to 1, it is 1. Here it is 0, 1, 0, 1, 0, right? So that means that here from 0 to 2, right? Again, after that, it's just repeating itself. So the first observation is that period of this function is 2, right? Every 2 units, right? It's just repeating itself. And it's a kind of piecewise function. From 0 to 1 is equal to 1. From 1 to 2 is equal to 0. Again, 2 to 3, 1, 3 to 4, 0. So how do you define this? We can define this as, let's say, e of t is equal to, here we have that's equal to 1 if t changes from 0 to 1, right? And that's equal to 0 if t changes from 1 to 2. That is how we discover this function, because p is quite defined function from the, what is it? It is graph. Okay. Now to solve this one, see here, what we know here is e of what, right? T plus, it is period. What is period is equal to 2. 2. That is equal to capital E of t. So immediately now I can apply, what is it? The previous theorem here. So then Laplace transform of this function, e of t, right? That's equal to 1 over 1 minus e to the power minus s, what is it? T. Actually, it's capital T, right? This should be capital T. All right, because here, when you substitute there, this should be capital T. All right. And all right, this is capital T. Why? Because of here, this is capital T. Okay. Capital T. Here, minus S times capital T. It is capital T, it is capital T. Okay, so here we have minus S times capital T. That's equal to minus our capital T is 2S times integral from 0 to capital T. That's equal to 2, right? And here we have e to the power minus st times our function, e of t. And here we have dt, right? And which is equal to, so from 0 to 2, from 0 to 1 is different function, from 1 to 2 is different function. And so here, from 1 to 2 is equal to 0. So we don't have to take this part. And that's equal to integral, sorry. First, I need to write this expression. Here we have 1 over 1 minus e to the power minus 2s, integral from 0 to 1, right? E to the power minus st. And when the function, actually t changes from 0 to 1, our function is 1. So here we have 1. So no need to write 1. Here we have dt. And from 1 to 2, right? 1 to 2, the function is 0. That's why here we have 0. Right? Just I need to evaluate this thing. And it's just a simple integral that's equal to 1 over 1 minus e to the power minus 2s. And if you evaluate this integral, that's equal to 1 minus e to the power minus s over, that is s, right? Because this thing is equal to minus 1 over s times e to the power minus st from 0 to 1. And I will substitute 1 and 0 to the function, and we will get the thing. Or if you just simplify this, here we got 1 over, here we have s times 1 plus e to the power, what is it? Minus s. Just multiply numerator and denominator by e to the power s, or e to the power, okay, this thing is 1, comes down, right? And after that, okay. Okay, because this one is, here we have 1 minus something squared. Here we have 1 minus a, right? Okay, we got this answer. That is how we evaluate periodic function. Guys, thank you very much. That is all, okay, for differential equations. I'd like to stop here. I wish you good luck. About your final exam, you will have a schedule next Thursday, okay, starting from around 10 or 10:20. Soon you will get email from me, maybe Monday or Tuesday. But what kind of question I'm going to ask? Theory, okay, like definition, something, and maybe true false questions or short answer required questions. Maybe solution also may be required, and also multiple choice questions. So this kind of question will come up to your in your final exam. And let me see if I ask easy questions, maybe around 20, more difficult questions 10. Okay, anyway, what you have to know is you have to review chapter 5, 6, and 7. All questions come from chapter 5 and 6 and 7. Okay, do you have any questions for me? All right, so if you have any questions, also you can text me, all right, in Telegram or send an email. Thank you very much. Wish you good luck. Bye-bye.